In this video, I want to take a look at limits and continuity for functions of more than two variables. And really the only reason I'm doing this separately from two variables is because that's the way our textbook is presenting it. And it was easier just to work with two variables to start with. But really, there's no difference. The stuff that we did with two variables pretty much just carries over to many variables. Let's take a look at limits. Back in Calc 1, for one variable, this was our definition of limit. L is the limit of f of x as x approaches a if for each epsilon bigger than 0 there exists a number delta such that if the difference between x and a is between 0 and delta, then the difference between f of x and L is less than epsilon. We gave a definition with two variables, but here's what it would look like for more than two variables, right? I'm going to let this vector capital X represent essentially a vector with all your variables in it. If you've got three variables, it might be x, y, z. If you've got many variables, you might call them x1, x2, x3, all the way up to xn, right? And then A is going to be the point that we're approaching. This is vector A, so it has as many components as you have in the space you're dealing with. So if it's in R2, then it would just be A comma B, a little a comma B like we did in the last video. Or, you know, if it's many dimensions, you might say A sub 1, A sub 2, A sub 3, all the way up to A sub n be the components of that vector. So you've got n variables approaching n particular numbers. And then those variables are being plugged into the function f, right? So this looks like a function of a single vector variable where the vector has n parts to it. So that's really a function of n variables, n real number variables. So anyway, we say L is the limit as vector x approaches vector A if for each epsilon bigger than 0 there exists a number delta such that if the difference between vector x and vector A is between 0 and n, that's the norm, the length of the vector is between 0 and delta, then the difference between f of vector x minus L is less than epsilon. And notice this L is still a real number because the output of a vector function, sorry, not a vector function, the output of a function of several variables is a real number. So this is a real number minus that real number, and we want that to be less than epsilon. If you're getting close to A, then f of x is getting close to L. Now, one thing that we should point out is that this, the norm of x minus A, is describing a set of points that are considered close to A, right? In one variable, this up here was describing a little line segment with A right smack dab in the middle and the radius of that line segment, so the distance from the center out to the two endpoints, is delta. When you're in two dimensions, this equation here is saying A is at the center of a little disk. Right? I don't say circle because the circle is just the edge. The disk is the whole filled in thing. So in two dimensions, this would be describing a disk of radius delta centered at A. In 3D, that would be a little ball. In 4D, it would be a, whatever you call it, a hyperball. You know, it's one dimension higher, but round, centered at A with radius delta. Okay. And all of the rules that we have for limits, that the limit of a sum is the sum of the limits, and the limit of a constant times a function is a constant times a limit, and all of those properties that you had for limits for one variable work for n variables. Right? So you take limits the way you would before. If you have a 0 divided by 0 situation, you might have to factor and cancel. I don't know of a L'Hopital's type rule for anything more than one variable. I'm not saying there isn't. It's not one thing I've ever run across. Anyway, you handle limits in the same way. Likewise with continuity. Here's our definition for continuity in one variable. We say that f of x is continuous at x equals a if the limit as x goes to a of f of x is f of a. If what happens as you approach A is the same as what happens at A, then it's continuous. You can draw it without picking up your pencil. For many variables, we have this vector x is a vector with n components in it, x1, x2, up to xn. So f of x is f of, it's got n variables being plugged in, each of the components of x. We say that this is continuous at vector x equals vector a if the limit as vector x goes to vector a of f of vector x equals f of vector a. If what happens as you get close to vector a is the same thing as what happens at vector a, then we say the function is continuous at x equals a. It looks very much the same. It's just that instead of having one variable, you have multiple variables going to multiple constants, right? And if this is true, then it's continuous. And notice, just as we had back here, this really implies three things. It implies that the limit has to exist, that the function value has to exist, and they have to be equal to each other. Okay? And all the rules that we had before are the same. If you add two continuous functions together, you get a continuous function. If you subtract two continuous functions, you get a continuous function. If you multiply them together, you get another continuous function. If you divide them, you get a continuous function as long as you're not dividing by 0. And if you're dividing by 0, then of course it won't be continuous because the function value won't exist because you can't divide by 0. Anyway, the calculations are the same as what we had with one variable or two variables. It's just more variables, but exactly the same concept. Anyway, there you go. There's limits and continuity for functions of many variables.